All right, let's take a look at more techniques of differentiation. Now, this technique is called the product rule. So if we're trying to take the derivative of a product, okay, now if the product could be multiplied together, you could get away without using the product rule, multiply the two functions together, get a new function, and then take the derivative. But generally speaking, if a problem is set up as a product, you'd want to use the product rule, and most of the time as you approach AP calculus, they're going to let you leave the product rule as is when you apply it and not have to simplify. So I'm taking the derivative of f of x times g of x. So the product rule says take the first function, leave it as is, times the derivative of the second function. And again, here I'm using operator notation. The derivative, I've got the brackets of the g of x inside of here with respect to x. So I'm taking the derivative of g of x with respect to x inside the bracket. So that's the first part, the first function times the derivative of the second, plus the second function unchanged. We don't do anything with it when we start off the second part. So plus the second function, in this case it would be g of x, times the derivative of the first function. So the derivative of f of x with respect to x. Now, the mnemonic device in remembering that is 1d2 plus 2d1. 1d2 plus 2d1, where the d stands for derivative. So I take the first function times the derivative of the second function plus the second function times the derivative of the first function. 1d2 plus 2d1. 1d2 plus 2d1. 1d2 plus 2d1. Okay, let's put this into action. We've got a function over here, and again, in this case, it's y equals, and we've got the square root of x times the quantity x squared plus 3. Now, in this case, we do have powers of x, so to speak. We know that we can rewrite the square root of x as x to the 1/2 power. I highly recommend writing radicals as power when you're doing the derivatives, so you can use the generalized power rule. Okay, so we've got x to the 1/2 power times x squared plus 3. Okay, and we're going to take the derivative using the product rule here, the 1d2 plus 2d1. Okay, so I'm going to use operator notation. dy dx equals 1, so that's x to the 1/2, times the derivative with respect to x of the second function. That's x squared plus 3. So I've got 1d2. So again, the derivative of the second one here. So 1d2 plus 2, so that's the second function unchanged, x squared plus 3. Now I need the derivative of the first. So the derivative of the first is the derivative of x to the 1/2 power. So I have applied the product rule. I haven't taken the derivative yet, but I've applied the product rule. I've got 1d2 plus 2d1 here. Okay, so now let's take the derivatives. And the reader at this point can see what you need to take the derivative of. I've got these operators here, which tells us that we still need to do calculus. We still need to take the derivative. So I've got x to the 1/2. Now I need to take the derivative of x squared plus 3 with respect to x. The derivative of x squared is 2x. The derivative of 3 is 0. So I've just taken the derivative of x squared plus 3. Notice the operators are gone. Once I've taken that derivative, we drop the operator. So I've got x to the 1/2 times 2x. Plus the second function, which is x squared plus 3. Now I need to take the derivative with respect to x of x to the 1/2. So that means I'm going to bring the half out front. 1/2 times 1, the coefficient would have been 1 to start with, times x. Now I've got 1/2 minus 1, which is negative 1/2. Okay, so in this step, the operators are gone, which tells the reader that calculus is done. Now, depending on how you want to convey your answer, I could multiply this all out, collect like terms. Okay, but as I have this set up, we've applied the power rule. Now, some people would say they don't want to have that negative exponent in that second term here. So let's change that. So I would have 1 over 2x to the half. That would be the same statement. When I take the x to the negative half, I move it to the denominator. It becomes a positive 1/2. Okay, and then maybe somebody says, well, I don't like to have the 1/2 power, so I'm going to change them back to square roots. So x to the half is the square root of x. Then I've got a 2x here, plus I've got that quantity x squared plus 3, and then I've got 1 over 2 times the square root of x. Okay, so again, I've got 3 different forms here, here, and here for that derivative. And again, keeping them separated because we use the product rule here, the 1d2 plus 2d1 here, okay, to get our answer. So I've got 3 different answers which would suffice. And again, no matter how elaborate the derivative looks, it still serves the purpose as the slope of the tangent line at any x value to the original function. And again, as long as it's defined in that original function. Okay, and again, I would have dy dx as I used here for my operator here. And again, that's the product rule, 1d2 plus 2d1.